So this is titled Blackbodies, Hot Gases, and Continuous and Atomic Spectra. We're going to look at a little bit at how hot objects give off light. And this is mostly for astronomy, but we'll talk about some other effects that we see as we talk about waves for geology as well. So we're going to define a few things. A thermal or blackbody radiator is just a hot object that gives off heat. Now, in the most general sense, as we saw in the last section, heat is just a form of light. And so it turns out that objects of any temperature are giving off light all on their own all the time. It's unlike the light that you see coming off my shirt. That's just being reflected off light from the light source in the room. This is light that's emitted by an object because of its temperature, and there are sort of mathematical ways of understanding that, which we'll get to just vaguely. We'll just talk about it very sort of not too quantitatively, just a tiny bit. So objects that these objects, we call them blackbody or thermal radiators. They're usually just a solid object. You can think of them as a hot poker that's been stuck into a fire, or if you've ever watched the TV show Cops, they use these cameras that detect infrared light. They see a human running down the street giving off light, infrared light. And so it turns out if you have something that can detect wave light of almost any frequency, you can detect it coming off a warm, solid object. And warm is very vaguely defined. Even if the thing is 100 degrees below zero, if you have the right detector, you can detect light coming off it. If the object is hot enough, like say you stick a poker in a fire, it'll glow red. If it's hotter still, it'll glow white. And then, if you have some kind of oxyacetylene torch, you can get something hot enough to glow blue. Stars are often this hot. And a lot of the stars in the sky are blue stars because they're so hot that they're glowing blue. Ours is glowing kind of whitish, looks a little yellow maybe. So I'm just going to talk about these guys for a second and how this works. Two objects made of the same material at the same temperature, the larger one will be giving off heat. That's just common sense. If I take a little piece of wood and light it on fire, and then I have a big pile of wood, there'll be more coming off the big pile than the little pile. But they have the same amount of heat coming off per area. The amount of heat per area is the same. The one with the bigger area produces more heat overall. And so often we're interested in this quantity here, the power per area. Turns out that's just proportional to this little sigma down here is a constant, the temperature to the fourth power. And that 4 should be a surprising number. The temperature of the fourth power means that if one object is 10 times hotter than the other, then the power emitted will be 10,000 times greater. Because if you remember, if you raise something to the fourth power, it's T times T times T times T, right? Well, if another object is 10 times hotter, it's 10T times 10T times 10T times 10T. That's what its power per area would be. And so it'd be a factor of 10,000, because if you multiply in any order, which you're allowed to do, you can multiply all those 10s together and you get a factor of 10,000. And so the amount of heat radiated by objects increases dramatically as their temperature goes up, because this T to the fourth here. If two objects differ in temperature by a factor of 10, but they have the same amount of energy available to produce heat, then the one that's 10 times hotter will last 1/10,000th as long, because it's burning energy 10,000 times faster, and if it's got the same amount of energy available, it's going to go through it 10,000 times faster, which means it'll last 1/10,000th as long. Stars do this. Stars can be 10 times hotter than, one star can be 10 times hotter than another, and will have a very short life by comparison to the other star. We'll talk about that as we go. Any hot, dense object like a piece of metal or even a star like the sun can be treated as a black body, and so these mathematical models that I just described work pretty well. It turns out that if you take a black body, just one of these thermal radiators, and you look at the amount of light coming off at each wavelength, you can graph that. And so let's look at this graph here. This is an object whose temperature is roughly the temperature of the sun. It's 5250 degrees Celsius. Right. This blue curve is an ideal curve, and the jagged curve is the sun. It's not quite a perfect mathematical model, but it's very close. And so there are a few things to learn from this. The wavelength is along the x-axis, so this is long wavelength, and this is to the left is very short wavelength. Similarly, these are the intensity. This is just kind of the amount of light, and you can think of the left to right here as the color of light. And these all objects, all black bodies, sort of emit this way. Notice there's a value of intensity for every frequency, right? It's a continuous line, and it decreases towards very high wavelength, and ultimately it decreases towards very short wavelength, and there's a peak in the middle somewhere. Right? This is called a black body radiation curve, and they all look very much the same. This one says the spectral distribution, intensity versus wavelength, of sunlight reaches the Earth's atmosphere as ultraviolet light, visible light, and infrared light. The unabsorbed sunlight at the top of the atmosphere has a distribution that approximately matches the theoretical curve of the black body at 5250 degrees Celsius, represented by the blue curve. I should say note that the curve for the sun is pretty close to that of an ideal black body. Notice that at very high wavelengths, on very large wavelengths, the intensity is decreasing, and at very small wavelengths as well. It turns out that the wavelength where the peak intensity occurs is predicted by Wien's law, which is given by this formula, which I won't make you use it, but we'll talk about it. I won't make you do any direct calculations from it. So there's the black body curve. The maximum of the curve shift to shorter wavelengths as the temperature increases. So let me just show you this. So here's an object that's been heated from 2500 Kelvin. Kelvin is not too different from the Celsius scale. I'm not too interested I'm not going to ask you to do any conversions between these two. They're off by about 250, 270 degrees. And so, the blue curve is the same as the blue curve from the previous graph, where it was at 5250 Celsius. This is now at 5500 Kelvin. So this was an object, not necessarily the sun, that was heated from 2500 to 3400 to 4400 to 5500. And this is the radiation versus, this is the intensity versus wavelength curve for these various. Notice that I want you to notice a few things here. Right? First, notice that when you heat the object from 2500 to 3400 degrees, the amount of light at every wavelength increases. That is to say, this pale curve, I don't know, is that yellow, is higher than the red curve everywhere. So when you heat the object, it's the intensity of radiated light increases everywhere. Notice also that this bottom curve is mostly just emitting in the red. So this is an object that's just hot enough to start glowing, and it's mostly just glowing here in the red. That's what you see as red. As you get hotter, now it's glowing more across other frequencies, and so it'll start appearing less red and more whitish. Right? It'll start moving away from red towards yellow and white. And so when you go from 3400 to 4400, notice the peak of the curve moves to the left. It moves towards shorter wavelengths. At 2500, it's here, which is maybe 1200 nanometers, and this might be 800 nanometers, and this might be 700 nanometers, and this might be, I don't know, 600 nanometers or something like that. And so the peak of the curve of the intensity versus wavelength curve. So the peak is where the brightest frequency is. Where the sun is, the brightest frequency is in the yellow, right in the middle. And now it's emitting almost as much blue as red. And so it appears white. It's almost got an even spectrum across, or at least a balanced spectrum across. If this thing continued to be heated, this object, and again it doesn't have to be the sun, eventually this peak would move outside the visible, and it would be emitting more blue than red. And so it would begin to appear blue as it got hotter than 5,500 Kelvin. So the peaks shift at shorter wavelengths as the temperature increases. Theoretical expressions as functions of temperature fit the observed experimental curves well. All right. Page 9. Scientists in the late 19th century struggled to understand light emitted by atoms. So now we've been talking about solid objects, and we're going to begin to talk about gases here. When dense objects like solids or liquids are heated sufficiently, they radiate some of the excess light. These are the thermal radiation curves that we've been seeing. These are these continuous curves. When you go back up here, for every wavelength, there's light emitted. This curve is continuous. And so if I just pick a random wavelength, this one, the red curve emits this much, the yellow curve emits this one much, the green curve emits this much, and the blue curve emits this one, and so on. We already said that the hotter it gets, the more it radiates at every frequency. That's why it's losing so much energy so much faster. Oops. Try that. Photons produced in this manner have a continuous range of energies, that's what we were just talking about, and thereby produce a continuous spectrum like a rainbow, in which an unbroken series of wavelengths is present. In contrast to the continuous spectrum emitted by hot dense objects, light emitted by hot gases appears as a discrete or atomic or line spectra, having very narrow line widths just interspersed throughout the spectral regions. So I'll show you an image of this. Let me see if I have one here. So if you were to take the light coming off the sun and run it through a prism, or maybe not the sun, but a hot dense object, you would have a continuous line, just like we said, because there's light being emitted at every frequency. That's what these graphs are telling you. At every single frequency, there's light being emitted. Every single wavelength, there's light being emitted. But this is what we see with gases. If you take the light coming off a heated gas, you no longer see this. When you run it through a prism, you see this if it's sodium, or this if it's hydrogen, or this if it's calcium, or this if it's mercury. Each type of glowing gas, each element in the periodic table produces its own unique pattern of lines. So the composition of a gas can be identified by its spectrum. So if you were to be looking at a hot gas through a telescope, you could run it through a little prism that would separate the colors, and then you could tell what it was made of. Now it might be made of more than one of these, but then they would just be stacked on top of each other and you could still figure it out, because these are uniquely sodium, these are uniquely hydrogen, these are uniquely calcium, and so if they were laid on top of each other, you could say, oh, that's calcium and hydrogen, or oh, that's calcium and sodium, and so on. Computers are very good at doing this sort of thing. Oops. So exciting a gas by heat or by other means at low partial pressure using an electric current or heating it will produce these types of spectra. Neon lights are an example of this. Fluorescent lights are kind of also an example of this, of how this is done. Each element in the periodic table, when heated this way, produces its own characteristic set of lines, its own fingerprint. If astronomers look at a very distant object and it gives off a hydrogen spectrum, they know it's hydrogen. That's how astronomers can know the composition of objects across the universe. Atomic spectra are a vital tool for astronomers and other scientists. It's how we know what stuff is made of that's very far away. So again, this is a hot, dense object. This is what you get with a star or a dense piece of metal or something like that. This is what you get with a gas. They look very different, right? This is after you've run it through a prism. If you look at sunlight, it looks yellow. And sunlight, I'm kind of cheating a little bit, and I'll tell you how in a minute. But it's hot, dense objects produce a continuous spectrum. Hot gases produce a discrete spectrum. If you look at a neon light, it looks like it's orange, but it's just because it's got a discrete spectrum that has a whole bunch of orange lines in it. And if you broke it down this way, if you ran it through a prism, then you would see that it's just a bunch of lines, mostly in the orange. So now there's a third type of spectrum. So here are the two types we've talked about. A continuous spectrum is when you take a hot, dense object, like a light bulb filament or the sun. A light bulb filament is just another piece of metal that's been heated up. Run it through a prism, and you get a full spectrum of colors. If you take a hot gas and run it through a spectrum, you get these lines here. Now here's the tricky one. If you take a hot, dense object like a light bulb filament, run it through a cold gas, and then through a spectrum, you get kind of this guy subtracted from that guy. It turns out that this gas pulls out the colors characteristic of it and from the continuous spectrum. So you see the continuous spectrum of the hot, dense object, and then superimposed on it you see dark lines of the cool gas that's between you and it. And that's called an absorption spectrum. This is the thing we're calling an atomic spectrum. You can call it an emission spectrum or a discrete spectrum or a line spectrum. It's got a lot of names. I'll usually refer to it as an atomic spectrum. That's what I'm saying here. So this one, that's the subtraction of the two, is called an absorption spectrum. So this is the absorption spectrum of the sun. And rather than being a single line that's a continuous rainbow, it's been chopped up and so it all fit on one screen. Otherwise we'd have a single line that was a rainbow, and it would be a mile long or something like that. And so this is the absorption spectrum of the sun. It starts up here in the blue, and it ends way down the opposite corner at the red, and just goes across and across and across. And you can see all these dark lines, and all these dark lines are characteristic of the atomic spectrum of the elements that are between us and the sun. So they're in our atmosphere, they're in the sun's atmosphere, they're in the gases between us and the sun. And we can use computers to match all these lines up with the corresponding atomic spectrum of those elements and figure out what is between us and the sun. What is the spectrum of the gases between us and the sun? And this is the way we discovered that people discovered helium, because there was an element that we weren't seeing whose spectral lines were in here. And they eventually found it and named it helium. Let me see. All right, that's a little bit about black bodies and atomic and continuous and absorption spectrum, hot gases and hot dense objects. See if you can answer a few of those questions.